Okay, in this video we're going to be looking at applications of maximum and minimum problems, and we want to be able to use the calculus skills that we've just developed and apply them to solve problems. Alright, let's just jump straight into some examples here. And pretty much the key knowledge that we're going to be drawing on, of course differentiation, but is going to be our theory on stationary points. So just a quick reminder, stationary points, or your local minimum or local maximum, occur when the gradient function is zero. So for applications of maximum, minimum problems, we're going to be referring to points where the gradient function is equal to zero, or dy dx is equal to zero. So let's begin. A metal cylinder has a volume of 300 millimeters cubed. Show that the surface area S of the cylinder can be expressed as S equals 2 pi r squared plus 600 over r. Alright, let's pull apart some of this information. We're trying to show surface area, and the formula for surface area is given by S, or of a cylinder. S equals 2 pi r squared, they're the two ends, and then the bulk is given by 2 pi r h. Alright, now as we can see, we're trying to show this equation here, which doesn't have this term, there's no h variable in this term at all. So let's use what we know about the volume to eliminate that h variable. So in other words, we're going to use the volume to come up with an equation. So let's just have a look at that. The volume is equal to 300 millimeters cubed, and we know that the volume is also given by pi r squared multiplied by h. So then if we just rearrange this formula a little bit, we get 300 over pi r squared, and all this is equal to h. Alright, so if we then substitute this into here, we can then eliminate the h term. 2 pi r squared plus 2 pi r times h, but h is equal to 300 over pi r squared. Okay, so the first part of the first term stays the same, 2 pi r squared plus 2 times 300, pi r times 300 divided by pi r. That leaves us with 600 over r, which is exactly what we wanted to prove here. Alright, so we've shown that the surface area of this cylinder is this here, with a relationship between surface area and radius. So what we're going to do is we're going to use that to find the radius that gives the minimum surface area of the cylinder. So, what does it mean to have a minimum surface area? Well, think about what the graph would look like. Minimum surface area would be a local minimum. And we know that a local minimum is a stationary point, and a stationary point has a value of 0 at the gradient function has a value of 0 at the stationary point. So minimum surface area is referring to a stationary point, or a point where surface area, or ds, what units have we got? Radius, so ds dr is equal to 0. So from above, our formula for surface area was given to us as, and we've proven it, 2 pi r squared plus 600 over r. Well, this is the same as, if we're going to find the derivative, let's express this in a slightly different way. 2 pi r squared plus 600 times r to the negative 1. And now let's find the derivative of this function. So once again, we're not writing dy dx, we're writing ds, or the gradient, or the change in surface area over change in radius. So we've got 4 pi r plus -1 times 600, and then r to the power of -2. Or ds dr is 4 pi r take away 600 over r squared. All right. Now, the radius that gives the minimum surface area is going to be where ds dr is equal to 0. So now let's equate this formula, 4 pi r take away 600 over r squared, equal to 0. So therefore, the minimum is at 0 equals 4 pi r take away 600 over r squared, or 600 over r squared is equal to 4 pi r. Or r cubed is equal to 600 over 4 pi. So let's just keep going over here. Our minimum value for r, our value for r, which gives our minimum surface area, is going to be the cube root of 600 over 4 pi. Or 3.63 millimeters. So our volume at the top was given millimeters cubed, which means our radius is in millimeters. And 300 was the 3 significant figures, so 1, 2, 3 significant figures there. So what have we just determined there? We've determined that the radius that gives the minimum surface area is 3.03, and we've done that by evaluating the gradient function at the stationary point. All right. Hence, find the minimum surface area of the cylinder. So what we have is the original relationship between radius and surface area, 2 pi r squared plus 600 over r. And we know that the minimum surface area occurs at a radius of 3.63. So what we're going to do is we're going to sub in r equals 3.63 to find minimum surface area. So S equals 2 pi 3.63 squared plus 600 over 3.63, which is equal to 248 millimeters squared. Once again, the 3 significant figures. Okay, let's have a look at a second example. See, we've got 2 bits of information. Given that x plus 2y equals 4, calculate the minimum value of, and then we've got a second equation there, x squared plus xy minus y squared. So let's just first say that what we're trying to do is we're trying to find the minimum, well, ultimately we're being asked to find the minimum value of this particular function. So let's call this, I might just call this function f. And what I'm going to do is to be able to derive this to evaluate the stationary point, the minimum value, the stationary point, we want to remove one of the 2 variables. So let's use this to remove one of the 2 variables. It won't matter which way you go, however, let's take away 2y from here to make x the subject, and that is going to be a little bit simpler in terms of the working. So this formula here can be rearranged to be x equals 4 minus 2y. All right. And what are we trying to do? We're trying to find the minimum p, or the minimum f. The minimum value for f is a stationary point. And at the stationary point, if we're going to be removing all of the x terms, making them all in terms of y, this is going to be where the df dy equals 0. Okay. So, first of all, let's expand and simplify our function f in terms of y. F equals x squared plus x y minus y squared. But we know that x is equal to this, so let's substitute this into here and here. 4 minus 2y squared plus 4 minus 2y y minus y squared. And now expand and simplify. 16 minus 16y plus 4y plus, 4y squared plus 4y minus 2y squared minus y squared. So this all simplifies to y squared minus 12y plus 16. Alright? So this is the same as this, where we've just substituted in an expression, or an expression in place of x. Perfect. So now what are we trying to do? Well, let's try and evaluate. Let's differentiate this to obtain df dy. Evaluate it at x equals 0 to then calculate the minimum value. So df dy is equal to 2y minus 12. And evaluating that at 0, 0 equals 2y minus 12, or the stationary point is going to be at y equals 6. So in other words, the minimum of our function up there is going to be at y equals 6. So to find, lastly, what we're being asked for, to find our minimum value of function f, let's substitute in 6 into our formula. 6 squared minus 12 times 6 plus 16 equals 36 minus 72 plus 16, or negative 20. So the minimum value of this is negative 20. Okay, let's look at one more example. The velocity of an electron in a magnetic field in meters per second is given by the function v of t is equal to 2/3 t cubed plus half t squared, take away 3t plus 4, given that t is greater than or equal to 0. Find the maximum speed reached by the electron. So once again, maximum speed, we're going to be looking at dv dt equals 0 to find time, and then we could sub that in to find the corresponding velocity or speed. So we're looking for essentially dv dt and where this equals 0 at the stationary point. So we've got our function up there, v of t. we have the corresponding dv dt, which is equal to t squared, sorry, 2t squared plus t minus 3. Taking the derivative of this function here. So now let's evaluate that at 0. At dv dt equals 0. 0 equals 2t squared plus t minus 3. And then factorising this, we get 2t plus 3t minus 1. And then solving for t, therefore t is equal to negative 3 over 2, and or t is equal to 1. Alright, so we've found the two stationary points. However, we're told that t is going to be greater than or equal to 0. So for that reason, we can disregard this value here. Okay, so what have we just found? We've found that the local maximum, or the max speed, is going to be when t is equal to 1, or 1 second has elapsed. So now let's actually calculate our max speed. Our max speed, we're evaluating our formula for velocity or speed at the value t equals 1. So 2 over 3, 1 cubed, plus 1 over 2, 1 squared, minus 3 times 1 plus 4. So 2 over 3 plus 1 over 2 minus 3 minus plus 4, so we've got plus 1. Or all in terms of 6, 4 over 6 plus 3 over 6 plus 6 over 6, or 13 over 6, which is equal to 2 and 1/6, which is equal to 2.1666, or 17 meters per second. In physics terminology, or meters per second. Okay. So let's just recap what we've looked at here. We've used what we know about stationary points to evaluate a derivative function of this original velocity function here. And then given this derivative function, we've taken that the maximum speed, or the local maximum, is going to be at the stationary point where dv dt is equal to 0. We've then evaluated dv dt equal to 0 here. We've discounted or disregarded the negative value for t, as t must be greater than or equal to 0, to determine that the max speed occurs at t equals 1 second. We've then substituted in t equals 1 into our original formula to then say that, evaluate or determine our maximum speed as 2.17 meters per second.